This screencast, I want to talk about graph traversal algorithms. For this screencast, you should have had some exposure to graphs before. I'm not going to spend a lot of time on the details. This is mostly for review for folks that have seen graphs with a few additional details that you may not have seen thrown in. So let me just remind you, there are two ways to traverse a graph, depth first search and breadth first search. The reason we'd use graph traversals is either to process something in the graph where we need to visit all the vertices and or all the edges. And the other reason is if we want to discover something about the overall structure of the graph. So depth first search, let me remind you, the way that works is you start at some vertex A in the graph, it could be anywhere, and you visit nodes in order of going down the tree. So you'll do depth first search on A, and you look at A's adjacency list, which in this case would be B and C, and you call depth first search on the first child, then you call depth first search on the first child of B, etc., and you're going down the tree. To do that, you'll use a stack either explicitly in your own code or implicitly, which is what we'll do most of the time, and just let the operating system and programming language use of recursion take care of all that for us. The second way is breadth first search. Here we visit all the children first. We don't go deep in the tree, we go across broadly in the tree. And so here we'd start at A, visit B, then visit C. When we visited B, we put it on a queue to save it, to know that we haven't finished with it yet. And so once we visit C, we also put that on a queue. Then we pull B off the queue, visit its children, pull C off the queue, visit its children. So, and typically the queue will be explicit in your code if you're writing a breadth first search, and we'll see that later. Let me remind you that when you learned about trees, you probably covered pre-order, in-order, and post-order traversals. Those are all a form of depth first search. Here's just a simple example to reinforce the concepts we talked about on the last slide. Here we're going to do depth first search on this graph, and we're going to start at A. And you can see we start out at A, we visit A, we go to its child, B, we look at B's adjacency list, we go to its child, D, and then we look at D's adjacency list, and it has an element on its adjacency list, C. Now all the vertices have been visited, and so we end up with that tree representation of the depth first search. If we do breadth first search, we also get a tree representation. Now we're going to start at A, and we do B first, then we do C, then we pull B off the queue, and we'll do D. So now we get this tree. So breadth first search and depth first search both produce trees, but they're going to, in most cases, they're going to be different trees. So here's some pseudocode for depth first search. Again, we're going to use a recursive algorithm for this. Let the operating system take care of the stack, and we'll assume that every vertex is unmarked, and we'll keep track of which vertices we visited by marking them. So here's the pseudocode. We call DFS on a vertex, we mark it as visited, and then for each J in the adjacency list, we do DFS on J. And that's all there is to it. So conceptually, depth first search is very simple. Here's some more detailed code, the way you'd probably actually want to implement something like this. We have a helper function, DFSG, where we can just pass in the graph. We'll have to initialize count. We're going to use that as our marker, basically, and as a timer. And we're going to keep track about whether we visited the vertex or not explicitly. Okay, and so all this capital DFS does is that for all the V vertices in V, if it's not visited, then we're going to call DFS. So the meat of the code is down here with little DFS, and that gets called with an explicit V. And what we're going to do is we're going to mark the vertex as visited, and then we may do some work. So this pre-visit V just is a stand-in for doing some sort of work that we're going to want to do when we first arrive. Then we'll update our timer count here, and we'll set pre-v. We're going to keep track of when we first got here. You'll see why later, to count. And then for each edge, V and U and E, if U has not been visited, then we're going to call DFS on U. After all the work, the traversal that goes on gets caused by the DFS, then you're going to come back here, and now you may want to do something to the vertex. Think of this as something you might do in a post-order traversal, and then update the timer and keep track of when that happened. So the order of the edges obviously is determined by the data structure here in terms of how you traverse the adjacency list, and that will determine exactly what how the nodes are labeled or are numbered. So that you can get different numberings depending on how the vertices are ordered or the edges are ordered in the data structure. So for us, when we do this by hand, we're going to always order the vertices the edges alphabetically. One other thing I should mention here that's important, notice this loop up here is important because what it does is if the graph is disconnected, then it will pick up the next connected component. So in an undirected graph, this is a pretty easy way to determine what the connected components are. And that's a good example of sort of the kind of global information that you get from this that may not be obvious if you just looked at the adjacency list or the adjacency matrix. So now I'd like to go through a more complex example in showing how the depth first search tree actually gets grown as we're traversing it. So we'll start off at vertex A and look at its adjacency list. Its adjacency list is B and E. So we'll take the first thing off the adjacency list. That'll be B. Then we look at B's adjacency list and we do depth first search on the first thing on its adjacency list. It has F and G on its adjacency list. So then B will call depth first search on F. And then F will look at its adjacency list. B has already been visited, so it'll ignore that. And it will then look at E, and it'll call depth first search on E. Now we'll be done with E, since the only thing on E's adjacency lists are A and F, and those have both been visited. So we'll walk back to F. F doesn't have anything on its adjacency list, so we'll walk back to B. B has G left on its adjacency list, so it'll call depth first search on G. Then G will call depth first search on the first thing on its adjacency list, which will be C. And then C will call the first thing on its adjacency list, which is D. And then D will call the first thing on its adjacency list, which is H, which I'll have to put over here. And then basically H will look at its adjacency list. D has already been visited, G has already been visited. So we'll be done with H. We'll go back to D. Then we're done with D, we'll go back to C. We're done with C, we'll go back to G, back to B. Okay, so we'll be here, and then finally go back to A. Okay, so this will be the depth first search tree for that graph. It's always a good idea to check things. Let's see, I have to make sure we've got all 8 vertices. 1, 2, 3, 4, 5, 6, 7, 8. So that's good. Now, the second thing, which I didn't take care of while we were doing this, was to think about the numbering. So when we first called it on A, we have a 1 as its pre-number. Then it would call it on B, so it would have 2. Then B calls it depth first search on F, that's 3. And F calls it depth first search on E, so that would be 4. E's done. Post number is 5. F's post number is going to be 6. And now we're at B, and we call G next. So now G's pre-number is going to be 7, C's pre-number is 8, D 9, H 10. We're done with H 11 post number. D's post number will be 12. C's post number will be 13. G's post number will be 14. B's post number will be 15. Run out of space here. And A's post number will be 16. Now I went over that pretty quickly, so take your time and make sure you understand where those numbers came from. So this picture shows it a little more clearly, the numbering. Same basic picture. Notice that I've drawn in 2 new edges here. These edges are the edges which were not traversed. If you recall, there was an edge when we went from A to B, and then F, and then E. There was this edge from E, between E and A, that was not used. And since we're E, we're going to draw this little arrow here, and we'll put this as an edge that was not traversed. This is called a back edge for reasons which I hope are obvious. A is an ancestor of E, so the edge is going between a descendant back to an ancestor. And here's another edge that was not used from H to G. And again, this is another back edge. It's going from a descendant from back to an ancestor. We'll study that. We'll spend a little more time on this when we get to directed graphs. But notice one thing, if you go back and look at the original graph, these are basically are part of a cycle. And when you run into a back edge when you're doing a depth first search, that indicates that the graph has a cycle. We'll do an application later where that's very important, and you'll get a little bit more practice with it. And B's adjacency list. So now we'll do depth first search on a directed graph. This gets a little more complex. We have to be very careful about what things are on the adjacency lists, especially when we're doing it by hand. So we'll start off here at A, and we'll look at its adjacency list. Well, it's got B, C, and F on it. So we'll go from A to B, and we'll look at B's adjacency list. And B's adjacency list only has one vertex on it, E. So we'll go there, and then we'll look at B's adjacency list, which is F, G, and H. So we'll go to the first vertex on E's adjacency list, which is F. Okay, so we've gone A to B to E to F. F only has one thing on its adjacency list, so we'll go to G. And then G doesn't have anything. So the first sort of branch of the tree is going to go A, B, E, F, G. And then we'll come back to F, and notice we won't use this edge because B has already been visited. So then we'll come back to E. E has something on its adjacency list, so now we'll get to H. Okay, H doesn't have anything on its adjacency list other than G, which has already been visited. So we'll come back to E, then we'll come back to B, and then finally we'll go back to A. All this part of the graph over here has been visited already. So now A will then go to C, and then go to D, and then be done. So if we look at this, okay, so now let's look more carefully at what happened when we did our depth first search traversal, and which edges we used. So we used the edge from A to B, and we used the edge from B to E. So let's just mark those off. Use that edge. We used B to E. If you look, then we also used E to F. We used E, F to G. Then we went back to E, and we used E to H. Then we went back to B, back to A, and we used A to C. And then we used C to D. Those were all the edges we used. So which edges didn't we use? Let's take a look at those more carefully. We did not use the edge from F to B. And if you look at that, that's going to be a back edge. So that goes from F to B. All right, so let's mark that off. And another edge that we didn't use was D to A. And that's also going to be a back edge. In other words, remember what that means. That means it goes from a descendant to an ancestor. All right, so, oh, I did forget to mark that one. So now, which other edges did we not use? We didn't use the edge from E to G. Okay, that's going to be a forward edge because that goes from an ancestor to a descendant. And let's see, that's E to G, that's there. And then we also did not use the edge from A to F. That's also going to be a forward edge. And now we still have a couple edges left to worry about. Let's see, that was A to F. So that's that one. And now let's see what other edges there are. There's one from D to H. It's going to be called a cross edge because it doesn't go either forward or backward. And then finally H to G. That's also a cross edge. So make sure you understand how these work and sort of the informal definition that I've given you so far in terms of what a back edge is. Goes from a descendant to an ancestor, a forward edge from an ancestor to a descendant, and a cross edge is just an edge that goes between two vertices that aren't directly related. Here's a picture with those just drawn in more carefully. So here's just on this slide we have more careful definitions of what's going on in a depth first search on a directed graph. In our case, we only had a tree, but in general you'll get multiple trees, and so we refer to that as a depth first search forest rather than just a depth first search tree. So tree edges are just the edges that involve visiting a vertex for the first time. Forward edges are edges from a node to a non-child descendant in the DFS tree. Okay, so as we've been saying, from a ancestor to a descendant that's already been visited. Backward edges go back to an ancestor from a descendant in the DFS tree. And cross edges are edges to a vertex that are neither an ancestor or a descendant. So just a quick review here. What have we got? Remember just that in a directed graph or digraph, every edge has a direction. So what does that imply? That implies the adjacency matrix is not symmetric, may not be symmetric. And the adjacency list, it only puts an edge in one, not two of the edge lists. While we're constructing this depth first search forest, you get 4 different kinds of edges: tree edges, forward edges, back edges, and cross edges. And just as in the undirected case, back edges indicates there's a cycle. And if you think about it, it's basically for the same reason that we had before, that as you start at the ancestor, you traverse down the tree to a descendant. There's obviously a path there, and then when you get the back edge back to the ancestor, you've got a cycle. Directed graphs without cycles are called DAGs. Those are really important. Directed acyclic graphs, those are really important. We're going to talk about them a lot during the course. and DAGs get used to model many different problems. This slide, I'm not going to say much about at this point, but we'll come back and use it when we're doing an application later, and I'll spend more time on it. But the idea is that each of the types of edges, the pre and post numbers associated with the edge, say there's an edge from U to V, the pre and post numbers are in a certain order. And the order for a tree or a forward edge is first you visit the ancestor, then you go down the tree and you visit the descendant, then you finish the descendant first, and you come back and then finally finish the ancestor. Think about the stack here. This basically is a reflection of what has to happen on the stack as you're traversing the tree. When it's a cross edge and there's no descendant or any other relationship between the nodes, then you just, the first node gets visited, it gets both its pre and post numbers. Then later you come to U, and there's this edge from U to V, and you visit U for the first time, and then you're done with V. So you get disjoint things. With a backward edge, again, if there's this edge from U to V, then the ordering is sort of the opposite from the forward edge. First, you're visiting the target V, and again, the edge is going from U to V. First, you visit that, then you go visit U, then you finish U, and then finally you go back to V. So the edge that you see going from U to V, you basically see it in between here. So that's just a prelude. We'll talk about this a lot more when we get to the applications of one of the applications of depth first search. So a quick summary. Remember, just to remind you some things about graphs that are going to be important. Depth first search can be implemented in graphs. If you use an adjacency matrix, it's going to basically take theta of the cardinality of V squared to do the traversal. If it's an adjacency list, it's going to be the cardinality of V plus the cardinality of E, the number of edges. There are two distinct orderings, when it's pushed onto the stack and the ordering in which they are popped off the stack. This is the pre-number, post-number. Lots of applications, some of which we'll talk about. Connectivity is going to be important. Checking if a graph is acyclic. You can use it to find articulation points, which are places where you can break the graph into pieces and connect by connected components, and just searching space problems. Depth first search gets used a lot in backtracking, which we'll talk about later in this course, and in many AI search applications.